Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I want to use this video to explain how you can actually calculate where the habitable zone would be for a planet orbiting a star. Now, I've done a few videos on the habitable zone, things like a variable habitable zone, how it changes, how different stars have different locations for that, but I've never actually explained how you calculate where it is. So that's what I'm going to do with this particular video. Now, just a recap, if you've come across this video and you haven't come across what the habitable zone is, or even if you do or you have come across it before, this is just going to be a bit of a recap anyway. So the habitable zone is kind of this zone, this area around a star where a planet can be located and it's hot enough to basically have liquid water kind of on its surface, or be present actually on the planet itself. So it has to be a set distance from that star for that to be the case. Because if it's too close, so in the red section here, if that planet was in that section there, it would be too hot. You're not going to have liquid water there. And in the blue section, the outer part, that's going to be too cold basically. It's too far away from the star. There's not enough energy from that star reaching the planet for it to then have liquid water. So this section in between, the green section, is the habitable zone, and we need to essentially find an inner edge and an outer edge to divide or define that particular zone. So, as I mentioned kind of in other videos and briefly at the beginning, different stars have different habitable zones. So the bigger the star, the more massive that it is, the more luminous, the more energy that it's giving out. Therefore, the planets have to be located further away to be at the right temperature. So for example, you've got the sun here, that has a habitable zone that is further away from it than the star below, which is a red dwarf. It's a smaller star, it's less luminous, it doesn't have as much energy being emitted, so the stars or the planets around that star have to be much closer. So it varies with the actual star type and how big and luminous that it actually is. So for example, a red dwarf star, you need to be very close to the actual star for a planet to be habitable. And red dwarf stars are one of the most abundant stars in the universe. Most habitable planets that we've found, or potentially habitable, in the habitable zone at least, are around red dwarf stars. The downside is they have to be very close. Red dwarf stars are known to kind of kick out loads of significant flares and stuff, which can actually distinguish life. There's a bit more to the story than that. But being close to the star, just to give you the temperature, is not always a good idea. They might also be tidally locked as well, because they're so close. The tides from the star will slow the rotation down quite significantly, so they're tidally locked. Now, a more massive star gives off a lot more energy. They are a lot more luminous. They are obviously more massive, as in like physically have more mass. So the planets orbiting these stars need to be much further away. There's a lot more energy being given off by the star, so it has to be further away. Now, there's something else worth noting, which is not taken into consideration for any of these calculations, because this is just a really rough calculation. It's the wavelength of light the star gives off. As they get hotter, they are emitting at different wavelengths than the cooler stars. That obviously is important for life as well. But anyway, just purely from temperature side of things, you've got to be further away the more massive and hotter that the star is to basically be habitable. Now, this is the HR diagram. It's the Hertzsprung-Russell diagram. If you haven't come across it before, it's a scatter plot of stars where you've got the surface temperature of the star and its luminosity. And when you plot all of those, you get distinct groups, basically. And why have I kind of shown you this? Well, actually, what we need to know to make this calculation for the habitable zone is the luminosity. Now, this is obviously from measurements. So if we have a star, we'll have a luminosity or a brightness associated with it, a stellar type. We can basically derive that luminosity from that. So that y-axis there is your luminosity, how much energy is being given off by the star against its surface temperature. And yeah, you've basically got distinct groups there, which can kind of help with the evolution of stars. But that's a different story completely. So we need luminosity of the star to start our calculation. Now, the starting point typically is the luminosity of the sun. Like lots of astrophysics and astronomy, we use kind of local reference points for units, because if you look at the actual luminosity of the sun, it's a big number. It's 3.83 times 10 to the 26 watts. That's a huge number, but that is the luminosity of the sun in watts. Now we give it the unit of L, and then you have this kind of circle with a dot. That circle with a dot denotes that it's a solar unit. So one of those is equal to 3.83 times 10 to the 26 watts. We do the same thing for radius. We might do R circle dot as well. So we use the sun as a reference point for other stars, because otherwise we get these really stupid big numbers that are difficult to kind of comprehend. So we would then compare other stars to that. Now let's say this other star here. Again, we denote other stars, luminosity wise anyway, by the star kind of symbol. So the L star is equal to 2 times the solar luminosity. So that basically means that this star here is twice as bright. So we've got a star here that is twice as luminous as the sun, and that's how we would write it essentially. It's 2 times a solar unit. So once we've got that, we can then use this equation to calculate our inner boundary for our habitable zone. And this is where it starts to become too hot to have liquid water. So basically we've got the square root of the luminosity of the star in solar units over 1.1, and then we multiply that by AU, which is the, well, not multiply it, but that the units it's given in is astronomical units. 1 astronomical unit is the distance, average distance of the Earth and the sun. So basically we can get the inner edge of the habitable zone in astronomical units using this equation if we know the luminosity of the star in solar units. So let's say it was twice, we'd put 2 divided by 1.1, square root it, and that would give our answer basically. And then we do something similar for the outer edge. This is where it's going to be too cold for liquid water. This time round, it's basically the luminosity of the star divided by 0.53 square rooted, gives us our outer boundary in AU as well. So, as I mentioned before, that L star is the luminosity of the star in question that we're using, and it's in terms of the sun. So if it's basically, if it's a solar-like star, sun-like star that's got 1 solar luminosity, it would be 1, essentially. And then AU, as I mentioned again, that's an astronomical unit. That's the average distance between the Earth and the sun. So again, it gives context to this distance instead of putting in meters or kilometers. We know that like 2 AU is twice as far away from the star than the Earth is. So that kind of makes sense. We understand what that number means then. So then, for a sun-like star, a solar-like star, we're going to put 1 in there for the luminosity. And if we do that, our inner edge for our habitable zone comes out at 0.95, so just a little bit closer than we currently are in our orbit. And the outer edge is 1.37 AU. So putting those numbers in for our sun, I suppose, gives us this kind of boundary here. And you can see that the Earth is in that habitable zone, which is good, I suppose. We'd be a bit confused if it wasn't. And for a star that is twice as luminosity, or twice as luminous, I should say, not luminosity, twice as luminous as the sun, we get these numbers out here. So the inner edge then obviously it creeps outwards, which makes sense. It's got to be further away now because the star is more luminous. It's now 1.29 AU for the inner edge and just under 2 AU for the outer edge. So our habitable zone has moved out because our star is now more luminous. Now, it's worth noting that this is pretty rough. This is purely taking into consideration kind of just the energy that's kind of making it to the planet, that sort of thing. It does not take into account any additional heating the planet might receive. For example, you've got Io, which is Jupiter's moon there, receives significant internal heating from tides from Jupiter. That would make, well, it would actually extend the habitable zone. There's other kind of reasons, there's kind of atmospheric things, greenhouse effects. They can all affect where a planet might be habitable. So it's a very rough calculation, but it gives you kind of a bit of a ballpark figure, you know, if it's roughly there or not. So thank you for watching. If you enjoy the video or find them helpful, then do consider becoming a member of the channel. There's extra videos in the member section, but it also helps support the channel. So thank you for watching.